see that. Hold on. There we go. So our lecture and our recitation on Turing reducibility was in some sense a high point mathematically, because we came to some conclusions about Turing reductions, which are very important and were used throughout computer science. But I wanted to give you some comments about how we teach this. In fact, how most mathematicians and computer scientists teach this is that if you're trying to show things are undecidable or NP complete in a generalization, you can get caught up in trying to prove the contradictions, which can be convoluted. Nothing wrong with doing that. But the goal of these reductions is that we give you a recipe by which solving the problem of determining something is uncomputable is changed into a mere programming problem. So if you look at this flow chart here, of course, you can't write a quiv. You don't know that at the time you're doing this, but Turing reduce, this is an eminently computable function. And in fact, some people think this is an abstract exercise in transforming a function f and an argument a into a pair of functions g and h. But in fact, the function that does that is something you can test, you can run, you can debug. And because we've done the logic for you, we have a recipe, kind of like induction. So all you need to do is write the purple box on the left. And then if it satisfies the spec, then you have a halting problem proof. So this is a nice position to be in if you're a computer scientist, because the task of proving something is uncomputable is, perhaps somewhat paradoxically, transformed into the problem of writing a reduction, namely a transformer function. Eminently computable, eminently testable, eminently debuggable using all your programming skills. And as a computer scientist, it seems to me whenever we have the task of writing a program, that's usually solvable, whereas math problems can be very hard. So we take a hard math problem, we transform it into the task of merely writing this transformer function. As soon as the transformer function can be shown to implement the spec, the many-one spec, we're done and we have a reduction, we have a proof of uncomputability. And then finally, as icing on the cake, this is the same mechanism we use to show NP completeness, which will be a major topic in 330, although not a major topic in our class here. So I just wanted to point out that this is what you need to write, and then the logic has been done for you once you've transformed a halting problem function into a pair of functions like this. It takes some ingenuity to do it, but it's mere programming. So not something that's beyond the pale, so to speak. All right. Okay, so I just wanted to make some comments. We're happy to talk to you more about this and how it works. I now would like to talk more about probability. So this is a new segment of the class. And students coming in have a variety of backgrounds. Some have seen a lot of probability and some combinatorics, others have seen none. I'm trying to bring us all up to speed. It's absolutely essential to use. So probability is super important in computer science and science in general. And of course, for problem set 6, we're going to integrate our knowledge of programming, functional programming, and probability together. The reading for this is quite good. It's on the web. Please take a look. I want to start with a little, really an